Hello guys, welcome back. So this is the last lecture for Module 3. In a previous video, we discussed the different criteria for spontaneity, and I introduced two new state functions such as the Gibbs free energy and Helmholtz energy. Now that we know the main characters in thermodynamics, it's time for us to relate these functions to each other. In this video, we will look at the different relationships of state functions and path functions that we use in thermodynamics. That is, we will look at the equations relating Gibbs free energy, pressure, enthalpy, entropy, internal energy, Helmholtz energy, and temperature. To start this lecture, we will look at some basic mathematical principles that we will apply in the derivation. Then at the last part of this video, I will teach you an easy shortcut on how we can remember all of these equations. Alright, so let us start by reviewing the concept of partial derivatives. So we know that the partial derivative of a function with more than one variable is the slope of the function with respect to one of the variables while all other variables are being held constant. Recall from your math courses that the partial derivative can tell us two things. First, it may show us how the function changes when one variable changes, and second, it may be used to determine how the function changes when more than one variable changes by an infinitesimal amount. Thus, if z is expressed as a function of two variables, let's say x and y, then the total differential dz can be written as the partial derivative of z with respect to x at constant y dx plus the partial derivative of z with respect to y at constant x dy, which is shown in this equation. Well, now if I write this term as m and this term as n, then the equation can also be expressed as dz is equal to m dx plus n dy. Now remember that m and n are functions of both x and y. This equation is an exact differential if and only if dm, that means the differentiation of m with respect to y at constant x, is equal to dn, or the differentiation of n with respect to x at constant y. Okay, so the next thing that we have to recall are our state functions as shown in this table. You can see here a summary of the state functions that we have discussed in the previous lecture video, and recall how we define the state functions as shown in column 2. From their respective definitions, we can take the derivative of these equations as shown in the third column. Now, these differential forms are important because we will use this in our derivations in this video. From these differential forms of the state function, they are then associated with the natural variables to which these state functions are dependent. So we have discussed actually this one in the last video. We have also discussed previously the conditions of the state functions for spontaneous processes. Now take note that these conditions are shown in column 4. Before we start with the derivations of the Maxwell relations, it is useful to combine the first and the second laws into a single mathematical statement. In order to do that, let us recall the first law of thermodynamics, which is shown here. The second law of thermodynamics is defined as the change in the entropy is equal to Q reversible over the temperature. And for a reversible change, it follows that dQ rev is equal to T ds. Now, for a reversible expansion PV work is equal to negative P delta V. Combining these equations for dQ and dW to the first law of thermodynamics equation will give us this expression. This is known as the fundamental equation. What we've just carried out gave us an extraordinary powerful result. This differential for du can be used to simplify the differentials for enthalpy, Helmholtz energy, and Gibbs free energy, as we will see in this lecture video. Now let's examine closely the internal energy U, whose differential form is du is equal to TdS minus PdV. Notice that internal energy U is just a mathematical function with variables entropy and volume. Hence we say that entropy and volume are natural variables of internal energy U as shown in this notation. The total differential of this function can be written as shown in this expression. These subscripts indicate that it is constant during the derivative. Also, by inspection, that is, comparing the two expressions for du, it is apparent that the partial derivative of u with respect to S at constant volume is equal to temperature, and the partial derivative of internal energy with respect to volume at constant entropy is equal to the negative of pressure. Okay, so at this point, we are now ready to derive the first Maxwell thermodynamic relationship. We already know that the internal energy, U, is an state function, and this particular expression here is an exact differential. Now, we are going to apply the idea about exact differentials to derive the first Maxwell equation. So, the consequence of this is that we can write the partial derivative of temperature with respect to a variable volume, and this should be equal to the partial derivative of the negative of pressure with respect to the variable, which is entropy. Now, if we look at the left-hand term, we have to keep entropy constant, and in this right term, we have to keep the volume constant. This is the first Maxwell thermodynamic relation, and we will derive the remaining three other Maxwell relations using this identical technique. Now let's look at enthalpy and derive another Maxwell relation. Recall that enthalpy H is defined by this equation, which is just the internal energy U minus PV. Next is that we have to define the differential of enthalpy, which is just going to be the change in the internal energy du, and we have to apply the product rule for PV term, which is T times the differential of the second term V plus the second term V multiplied to the differential of the first term, or dP. Recall that the fundamental equation can be written as du is equal to T ds minus P dV. We now substitute the expression for du into our expression for dH, and this gives us the following equation. We can immediately notice here that we can cancel out the P dV terms, so we're left with this expression, that is dH is equal to TdS plus VdP. This equation tells us that the changes in enthalpy is dependent on the changes in entropy and pressure. So we can simply say that the natural variables for enthalpy are entropy, S, and pressure. So we can simply write this as enthalpy is a function of entropy and pressure, which is shown in this notation. Alright, so we know that enthalpy is a state function, and we can write the total differential of the state function in terms of the variables entropy and pressure as follows. The next step that we will do is to set the two differential equations equal to each other, that is dH is equal to dH. Since there are terms in both equations that are of the same variables, let's say ds and dP, this means that the coefficients have to be equal. Immediately, we have the partial derivative of H with respect to entropy at constant pressure is equal to temperature. We can also say that the partial derivative of H with respect to pressure at constant entropy is equal to volume. Now, we make use of the fact that since enthalpy is a state function, we can write its differential as an exact differential. Since dH is an exact differential, we know that the derivative of temperature with respect to pressure has to be equal to the derivative of the volume with respect to entropy. Now, looking at the left term, since pressure is changing, the entropy has to be constant. And in the right term, since entropy is changing, then the pressure has to be constant. Now, this will give us the second Maxwell thermodynamic relation from enthalpy. Okay, so let's recall the Helmholtz energy, which is defined as A, is equal to the internal energy U minus Ts. Again, the next thing we have to do is to find the differential of dA, which is just going to be du, and we have to apply again the product rule for Ts, which is T times the differential of the second term S minus the second term multiplied with the differential of the first term. Now, recall that the fundamental equation can be written as du is equal to TdS minus PdV. We got this from the combination of the first and second law. Now, we substitute the expression for du into our dA expression. So this will give us the following equation. Notice that immediately we can cancel out the TDS term, so we are left with this expression, which is dA is equal to the negative PDV minus SDT. This term tells us that the change in the Helmholtz energy is dependent on the changes in the temperature and volume. We can say that the natural variables of Helmholtz energy are volume and temperature, and we can write this in the following notation, which is A is a function of volume and temperature. Now, the Helmholtz energy is a state function, so we can write the total differential of this equation in terms of the variables volume and temperature as follows. The next thing we can do here is to set the two differential equations equal to each other. That is dA is equal to dA. Again, since there are terms that are in the same variable, let's say dV and dt, this means that the coefficients have to be equal. Immediately, we have the partial derivative of A with respect to volume at constant temperature is equal to the negative of pressure. Now, we can also say that the partial derivative of A with respect to temperature at constant volume is equal to the negative of entropy. Now, we make use of the fact that Helmholtz energy is a state function, so we can write it as an exact differential. Since dA is an exact differential, we know that the derivative to the negative of pressure with respect to the change in temperature has to be equal to the derivative of the negative of entropy with respect to the volume variable. Since the temperature is changing in the left term, then the volume has to be constant. And since the volume is changing in the right term, then the temperature has to be constant. Now, we just have to cancel out the negative signs in both sides of our equation, and this will give us the Maxwell thermodynamic relation coming from Helmholtz energy. Alright, so let's look at the fourth Maxwell relation using the Gibbs free energy. Recall that the definition of Gibbs free energy is G is equal to H minus Ts. We can write the differential of the Gibbs free energy equation as dG is equal to dH minus Tds minus S dt. Again, I have used the product rule for the last term. Recall that from our differential form for enthalpy, this is given us by this equation, which is du plus pdv plus vdp. If we substitute the dH expression to our dG expression, I will get this equation. For a closed system doing a non-expansion work, we can replace the du by the fundamental equation, that is Vu is equal to Tds minus SDT. And substituting this to our dG equation will give us this longer equation here. Okay, so now we can immediately notice that some terms in this equation cancels out, and we can remove the TDS and PDV. This will now give us a more simple equation, that is the infinitesimal change in the Gibbs free energy is equal to the VdP minus SdT. This expression shows that the change in the Gibbs free energy is proportional to the changes in pressure and temperature, and suggests that the natural variables for Gibbs free energy are pressure and temperature. In your textbook, this is referred to as the fundamental equation of chemical thermodynamics because it relates thermodynamics to chemistry, because temperature and volume are the usual controllable variables when we do experiments. Alright, so we can now write the total differential of this equation as follows. Just like what we did earlier, we can set the two dG equations equal to each other. Since there are terms of the same variable dP and dt, this means that the coefficients have to be equal. We can say that the change in Gibbs free energy with respect to pressure at constant temperature is equal to volume. And similarly, we can say that the change in Gibbs free energy with respect to temperature at constant pressure is equal to negative of entropy. Alright, so we know that the Gibbs free energy is a state function and dG is an exact differential. As a consequence, we can use the differential form of this equation to get the fourth Maxwell thermodynamic relation. So applying the exact differentials we will obtain that the partial derivative of V with respect to T at constant P has to be equal to the negative of the partial derivative of the entropy with respect to pressure at constant temperature. And this is the fourth Maxwell relation. Okay, so before I summarize the Maxwell relationships, remember that Gibbs free energy, or G, tends towards a minimum for systems held at constant pressure and temperature. Also, there are so many processes that are performed at constant temperature and pressure, example chemical reactions in the laboratory, and the Gibbs free energy is an extremely important quantity that indicates to what state systems will evolve. Example, in which direction, to what extent a reaction will proceed. So Gibbs free energy is a state function that will be the focus in the next, or the star in the next module of our course. Okay, to summarize what we've learned, these are all the equations that we've derived, and these are called the Maxwell relations, and we will use them in the next module. Alright, so far, after having gone through all the detailed derivation of the Maxwell's relations and identities, it would be difficult to remember these equations at an instant. Actually, there's no need for us to memorize all of these equations in the first place. We have a device or an easy way to remember all of these equations. In the last part of this video, I will teach you an easy mnemonic to remember these equations using what we call as the thermodynamic square. Now, there are several versions of this thermodynamic square that you can search in other references, but I have modified this square to make it easier to use. Okay, so the first thing we have to do is to construct the thermodynamic square, and this is essentially a 3x3 table as shown here. Now the next thing is how to arrange the state functions and pressure, temperature, and volume in this table. We have the simple mnemonic that will aid us to do this job. Alright, so remember this sentence: good professors have studied under very amazing teacher. Notice that I have highlighted the first letters of each word in the sentence, and this should already give us an idea of what this letter symbolizes. G stands for Gibbs free energy, P for pressure, H stands for enthalpy, S stands for entropy, U means internal energy, V is for volume, A is for Helmholtz energy, and T is for temperature. Okay, so by the way, just a piece of information before we carry on. Why is Helmholtz energy given with a simple capital letter A? So remember that Helmholtz energy is the maximum work that the system can do to its surroundings. So the letter A came from the German word Arbeit, which means work. Alright, so the next step that we have to do now is to put the state functions in proper positions on our thermodynamic square. So we start with letter G at a 12 o'clock position, then we place P to the right, and we will continue filling up the square in exact order of letters in the mnemonic and making sure that the center of the square is empty. In other words, we will place the exact order of letters in a clockwise manner, as shown here. Okay, so when we are done positioning the letters in our square, then we are ready to use this to derive our Maxwell thermodynamic relations. Alright, so I will just highlight specific rules as we go along with this video. Okay, so let's look at the first Maxwell relation. Now, watch carefully how I use the thermodynamic square to get the first relation. I will start using the left-hand side of the column of the square. I will draw an arrow starting from the top, which is temperature, or T, and goes down to bottom, which is volume, or V. Alright, this is now my partial derivative part, which is partial T over partial V. Now, we have to find the function that is maintained constant. To do this, I will draw a diagonal arrow from the temperature that goes along the opposite corner, which is entropy, or S. This is my constant for the partial derivative term. Okay, so now let us find the partner of this term. So we do a similar technique, but this time I will use the right-hand side column of the square. Starting from the top, which is pressure, or P, I will draw a line that goes all the way to the bottom, which is S or entropy. Again, this will be my partial derivative term. So I will have partial P over partial S. Alright, so to find the function that is to be held constant, we draw again a diagonal line from where we started, which is P. And this diagonal line goes along the opposite corner, which is V. Therefore, V is my constant. Now, to use this square, when the functions P and S comes together, we will put a negative sign. Alright, so this is the first relation of the four Maxwell equations. Alright, so this is just to give you a summary of the movements that we did in the thermodynamic square to get the first Maxwell relation. Here are some important points that you have to remember. We use the first and third vertical columns to get the partner partial differentials. Second, we start at the top of the column to get the numerator of the partial derivative. Third, we go all the way to the bottom to get the denominator of the partial derivative. Fourth, to find out which function is to be kept constant, we start from the top or the function where we started and draw a diagonal opposite line until the corner. Lastly, when P and S comes together in a term, we will put a negative sign on that side of the equation. Okay, so I will jump to the fourth Maxwell relation. Well, this is just to make our understanding of the thermodynamic square clearer. Again, watch carefully on how I use the thermodynamic square. I will again start in the left-hand side of the column of the square, but this time I will reverse the first movements that I presented earlier. I will draw an arrow starting from the bottom, which is V, and goes up to the top, which is P. Alright, so this is now my partial derivative, which is partial V over partial P. Now, we have to find a function that is maintained constant. To do this, I will go back to where I started, which is V, and draw a diagonally opposite arrow until the corner, which is P. This is now my constant for the partial derivative term. Okay, so now let us find the partner of this term. And we do a similar technique. I will use the right-hand side of the column of the square. Starting at the bottom, which is S or entropy, I will draw a line that goes up to the top, which is pressure. This will be my partial derivative term. I have now partial S over partial P. Again, to find the function that is to be held constant, I will draw again a line, a diagonal line from the function where I've started, which is entropy, and this diagonal line goes along the opposite corner, which is temperature or T. Therefore, temperature is my constant. Now, similar to the first relation, when the functions P and S comes together, we will put a negative sign on the that side of the equation. Alright, so this is the fourth Maxwell relation. Okay, so this is just to give you a summary of the movements that I did in the thermodynamic square to get the fourth Maxwell relation. Here are some important points that you have to remember. First, we use the first or the left-hand side and a third or the right-hand side columns to get the partner partial differentials. We also start at the bottom of the column to get the numerator of the partial derivative, and then we also go all the way to the top to get the denominator of the partial derivative. Now, to find out which function to keep constant, we start at the bottom or the function where we started and draw a diagonally opposite line until the corner. Lastly, when P and S, or when pressure and entropy comes together in a term, we put a negative sign on that side of the equation. Now let us look at the second Maxwell relation. Take note that the movements that I will present are now slightly different from the first two relations that I've presented earlier. Watch carefully on how I do this movements. Instead of the right hand and left hand columns, we will focus our attention to the top and bottom rows. Okay, so I will now draw an arrow starting from the top left corner, which is temperature or T, and this goes to the other end of the same row, which is pressure or P. All right, this is now my partial derivative. So I have now partial T over partial P. Okay, so the next thing we have to do is to find the function that is maintained constant. To do this, I will go back to where I started, which is temperature, and draw a diagonally opposite arrow until the corner, which is entropy or S. So this is now my constant for the partial derivative term. Okay, so now let us find the partner of this term, and we do a similar technique. I will now use the bottom row of the thermodynamic square. Starting at the bottom corner, which is V or volume, I will draw a line that goes all the way to the other corner of the same row, which is entropy or S. Again, this will be my partial derivative term. Now I have a partial V over partial S. To find the function that is to be held constant, we will draw again a diagonal line from the function where we started, and that is volume. Okay, and this diagonal line goes along the opposite corner, which is P. Therefore, pressure is my constant. Notice that in both sides of the equation, P and S either appeared as a partial derivative or a constant. Hence, we will put a negative sign on both sides of the equation. However, we can cancel these negative signs, and ultimately we'll get the second Maxwell relation. Alright, so this is just to give you again a summary of the new movements that I did in the thermodynamic square to get the second Maxwell relation. Here are some important points that you have to remember. First is that we use the top and the bottom rows to give to get the partner differentials. Then the first function where we started becomes the numerator of the partial derivative. Then we go all the way to the other end of the same row to get the denominator of the partial derivative. Okay, so to find out which function to keep constant, we draw a diagonally opposite line from the function where we started until the opposite corner. Lastly, when pressure, P, and entropy or S comes together in a term, we will put a negative sign on that side of the equation. In this case, since both P and S occurred on both terms of the equation, then obviously the negative sign will cancel out. Finally, let's look at the third Maxwell relation. Now I will draw an arrow starting from the top right corner, which is pressure or P, and this goes to the other end of the same row, which is T or temperature. Okay, so this is now my partial derivative, which is partial T over partial P. Again, we have to find the function that is maintained constant. To do this, I will go back to where I started, which is pressure, and draw a diagonally opposite arrow until the corner, which is volume. This is now my constant for the partial derivative term. Alright, so now let us find the partner of this term, and we do a similar technique. I will use the bottom row of this square. Starting from the bottom corner, which is entropy or S, I will draw again a line that goes to the other last function of the same row, which is volume. Again, this will be my partial derivative term. So now I have partial S over partial V. Okay, so to find the function that is to be held constant for this term, I will draw a diagonally opposite line from the function where I started, and this line goes along the opposite corner, which is T or temperature. Therefore, temperature is my constant. Okay, so now notice that in both sides of the equation, P and S did not appear together, so there is no need to write negative signs on either sides of the equation. So finally, this is a third Maxwell relation. Alright, so this is just to give you a summary of the new movements that I did in the thermodynamic square to get the third Maxwell relation. Alright, so now let's look at how we can derive the other Maxwell thermodynamic identities. In order to do this, we have to make some slight modifications in the movements that I discussed earlier. This time, we will start at the functions found in the middle of the columns and the rows and move to either left or right of the same column or row to find the differential. Now, the function that will be held constant is also found in the same column or row. Then we have to draw a diagonal line directly opposite from the last function we identified in order to find the coefficient to which the differentials can be equated. Okay, so remember now that pressure and entropy will only have a negative sign if they become coefficients, not if they are not part of the differentials or constants. It sounds a bit confusing, but the movements are actually easy to carry out when you see the pattern. Alright, so let's use the first and second identities to illustrate these movements. So we start with these two thermodynamic identities that were co-derived from the first Maxwell relationship. So that these identities came from internal energy. So we start at the internal energy U, and this goes to the right, that is entropy. Since the volume is on the same row, then this function will be held constant. Now, to find the coefficient to which this differential is equal to, I will draw a diagonally opposite line from entropy going to P. Now, let's look at the second thermodynamic identity. We start again at the internal energy U, and this time we go to the left. So this function will be volume. So this will be my partial derivatives, partial U over partial V. Then, since entropy is on the same row, this will be my function that will be held constant. So obviously, this will be a positive value because this is held constant. Now, to find the coefficient, I will draw a diagonal opposite line from V going to negative P, or negative pressure. Alright, so continuing on, let's look at these two thermodynamic identities that were co-derived from the mathematical treatment of Gibbs free energy. Let's look at Gibbs free energy G. Let's go from the right function, which is pressure, or P. Since the temperature is found in the same row, this will be my function that will be held constant. Take note that I did not put a negative sign for pressure because it is a part of the differential. Now, to find the coefficient to which this partial differential is to be equal to, I will draw a diagonally opposite line from pressure going to volume, or V. Now let's look at another thermodynamic identity. So we start again at Gibbs free energy, and this time we go to the left. So this function will be temperature. Alright, since pressure is on the same row, this will be the function that will be held constant. Obviously, this will be a positive value because this is to be held constant. Now, to find the coefficient to which this differential is equal to, I will draw a diagonally opposite line from temperature going to negative entropy, or the negative S. Okay, now let's try to use the enthalpy, or H, and the arrow now goes to the bottom, which is entropy. Since entropy is part of the differential, this will not have a negative sign. So notice that pressure is on the same column, so this function will be held constant. I will now have a partial H over partial S at constant P. To find the coefficient, I will draw a diagonally opposite line from S, or entropy, going to temperature. Now, let's look at another thermodynamic identity. So we start again from enthalpy H, and this time we go to the top. So this function is pressure. So notice that the pressure is a part of the differential, and we will not put a negative sign on this function. Entropy was also in the same row, so this function will be held constant. I will now have a partial H over partial P at constant S. Now, to find the coefficient, I will draw a diagonally opposite line from pressure going to volume. All right, so this time we start at Helmholtz energy A, and this arrow goes to the bottom, or volume V. Notice that this temperature is on the same column, so this function will be held constant. Therefore, my partial derivative will be partial A over partial V at constant temperature. Now, to find the coefficient, I will draw a diagonally opposite line from volume going to the negative of pressure. Okay, so now let's look at the another thermodynamic identity. So we start again at Helmholtz energy A, and this time we go to the top. So this function will be temperature. Since volume is the same column, this will be my function that will be held constant. Now we have partial A over partial T at constant V. Now to find the coefficient, I will draw again a diagonally opposite line from temperature going to the negative of entropy. Okay, so all right, I suggest that you have to go over the movements that we did to get all the Maxwell thermodynamic relationships and their co-derived identities. So obviously you have to repeat practicing the movements that I demonstrated in this video for you to become more confident in deriving the Maxwell thermodynamic relations, and good luck with that one. Okay, so thank you very much, and this ends module 3.